Okay, for this lecture we got a lot to cover, so I'm going to move fast. There's different types of constitutional isomers. They're each mentioned in the book somewhere, but they don't delineate them very well in the chapter, so I'm just going to show you each of them. An ion exchange isomer. So here, to be an isomer, it needs to be, you need to have the original, and then something has the same formula, same number of atoms, but just the bonding is somehow different. Something happens that's different to make the structure different. So here we have the complex, or we have the coordination compound. If we were to exchange these, then we end up with this structure. And actually, you want to always draw it as, you want to draw it with the bonding as it actually is. The oxygen is the thing that gets bonded to, so sorry about that. And note that when we draw the structure, that we have the water. I draw the water backwards here to show the oxygens are the thing that bond to the chromium. Then we put this here. Now the charge on the chromium must have been +3, so now this is +1, and the chloride on the outside is -1. So it was +2, -2. We move the ion inside, now it's +1, -1. And you can look at that to verify that, but all we've done is change out the ions. There's ones inside of the coordination sphere, we call it, inside the complex ion, and ones that are just counter ions, and we've just switched them out. So they're different compounds, very similar but different, and they have different chemical properties. So you should be able to draw an ion exchange isomer, or an example of that. Coordination isomers. These are ones where all that we've done is, or appears to have done, that we've done is to change out the central ion in each, so we just switch this. Now it seems like a nice simple swap, but no, this would involve a huge amount of chemistry, so we don't really just go from one to the other, but we can create this one and we can create this set that will have completely, well not completely, but very different properties from each other. And so all that's really happened is that so if I give you this, you should be able to draw the coordination isomer of that one. Hydration isomers. Normally the thing on the outside has to have a charge to be, we can't just change out CO to the outside because the CO is a gas, it'll just go away. But water forms hydrates, so we can have this. We have Cl2 and then we dot it with 1 water. We can also go another step, H2O4, Cl2 inside, then Cl on the outside, and then 2 waters, so we have a dihydrate. And we can just keep going till we run out of things to exchange. So this is 3 Cl's inside, 3 waters on the outside. That's as far as we can go because there's nothing else to exchange out. We need to have a coordination number of 6 on the inside. We can't put take another water out because we'd change the coordination number to 5, so that's as far as we get to go. So if we move something in, we have to move something out. If we want to move something further out outside, then we need to move something in. Okay, linkage isomers. This one, I'll draw it out. So most of these complexes are going to have 6 sites, so you should get used to drawing this. You draw these 4 indicating a plane, this one above, this one below, and then we can put the ammonia, we got 5 of them, write the ones backwards that are, so that we can show that the nitrogen is always attached to the cobalt, and then we have this this nitrito ion, like this. But then we can also, and in the book they show the formula, they actually change the formula so that you can see that. Sometimes it's not so easy to do that. You actually have to draw the structure to see it, but we could, in this case, we have the ammonia and this time the nitrogen, the nitrogen is attached to the cobalt. You say, well, is there really that much of a difference? Not really, actually. They're only slightly different from each other. So it's very subtle, but there is a chemical difference. So since that's the case, we have to note that. We have to note that we are attaching this one with oxygen, this one with nitrogen. So that's a linkage isomer. Now, we get into the more subtle stuff now. That one was where we have we'll have different bonding. To create the other isomer, we see that we have atoms that are bonded differently to each other. But geometric isomers, the bonding is the same. It's just the orientation in space is different. We have this structure. We have the chlorines next to each other, but we can also have them across from each other. Or we can think of the ammonia as being across from each other. These are cis, and these are trans. This one is called cisplatin, common name, and this is transplatin. This one was the first chemotherapy drug. This one is nothing. It doesn't do anything, but they're geometric isomers. So, but you notice that the two chlorines are bonded to the platinum, two ammonia to the platinum. Same here. Two chlorine to the platinum, two ammonia to the platinum. So that's not enough information to distinguish them. What you also have to say is how they're oriented relative to each other. Chlorines are next to each other, the ammonia are next to each other, and here they're across from each other. So the bonding, describing the bonding, is the same. It's their orientation in space that's different. So how about this one? We can see that, I'm not going to draw all of them. Actually, no, I guess I am, because there's only two possibilities. We have the bromine across from each other. That's the trans form. Now, we don't talk about the waters as being cis or trans because there's 4 of them, but the bromines this is trans to each other, and then we can also have them as cis. Now, you might say, well, does the bromine, if we put a bromine here, do we put the other bromine here or here? Well, it's hard to see. In class, I'll use the molecular models, but they are exactly the same. So we can put them, as long as they're 90 degrees from each other, we can put them at either site, and then the waters fill in the rest. And that's it. That's the only 2 that there are in this case. And it looks like there might be more. Go ahead and try it. You try to find a different one. They should any that you come up with will be one of the other. This one or this one, and this one would be called cis. Again, just dealing with bromine, just the 2. Cis and trans, we're talking about 2 of the same species. So we can't talk about the waters as being trans or cis because there's 4 of them. Okay? Indicate how many geometric isomers there are for each of the following. So this one, for the waters, I'm not even going to draw this out. You can see that there's all of the ligands are the same. So there's only 1. So there's only 1 isomer that's possible. I'll use this for this one. We have chlorine here. So this one is a trivial one because there's no isomer, there's no ligands to change. They're all the same. So there can only be 1 geometric isomer. But for this one, looks like there might be more than 1. But if you move this chlorine here, then you can easily tilt this molecule back up to put the chlorine on top. So no matter where you put the chlorine, for another, what you might think is an isomer, you can rotate it back into the original form. And that's one of the definitions of the isomer. If you can't rotate it back into its original form, or you can't do some simple manipulation of the molecule that doesn't involve breaking of the bonds, and you can take one molecule and overlap it with another, then they're not geometric isomers. They're the same ones. For this one, we have, actually it's the same as this. If we make this chlorine, and this one chlorine, then there are 2. They're either trans or cis. So for this one, since there's 2, and it's always going to be one of these where it's one of these complexes where there's 6 spots, the chlorine can be across from each other, trans or cis, so there's only 2. Now for this guy, we got a little bit more going on. And this is, so we have the chlorine here, and we have a chlorine across from the other, and then here, and then we have the water. And you can see that these chlorines are in this great arc. You know, it's like if you put this right inside of a sphere that fit perfectly over these ligands, that we just be drawing right around the equator of that sphere. And this one is called mer, for meridian. This is the mer form of it. And then the other one, there's only two, even though there looks like there might be a whole bunch of them. If they're all next to each other, they're all within 90 degrees of each other, they're now on the face of this octahedron. So this one is called FAC, F-A-C. Those are the two that are possible when you have two sets, 3 and 3. So there's two possibilities here. Now, if we go to 4 waters and 2 chlorine, then it's the same as 2 chlorine and 4 waters as far as the number of isomers. Definitely different compounds, but there's no reason to go any further. We could just keep adding chlorines until we have 6 chlorines, and we'd be back to the same kind of thing as we had here. So no reason to go any further. Now this one is the one that I usually put on the exam. So as a heads up, this is the one I put on, and I ask how many isomers can you find for this one. I won't tell you because it's pretty easy to find out. There's not thousands. There's actually less than 10. And but just this is something that you should work on. And in class, I go through the same a lot of this as well, and I'll give you a better idea if you're in my class. So figure out how many you have that's less than 10, and you should be able to determine how many geometric isomers you have for that one. I won't say that because that's the one I always put on the exam, or something similar to it. Okay, then we get to even a more subtle type of isomer, because not only is the bonding the same, but the orientation in space is the same. So it's a little tricky to say, well, how can they possibly be different? Well, what we do is when we have these two molecules, what they are is we take one molecule and we look at its mirror image. So if we held that molecule up to a mirror, and then we built that molecule that we see reflected in the mirror, and we try to overlap them, then and they don't overlap, then they are optical isomers of each other. It's like with the hands. One hand looks like, I don't know if I'm fitting on here, but one hand is a mirror image of the other, but they definitely don't overlap perfectly. If you overlap them this way, the thumbs don't overlap. If you do this way, they're facing different directions, so they're not truly overlapping. So mirror image molecules that appear to be mirror images of each other that don't overlap are optical isomers. If we put one of the species into a solution, and we run polarized light through, that is, plain polarized light. When light comes through, say from the sun, it's angled it's rotated in all sorts of directions. The waves of light are all oriented differently. We put them through a polarizer, though. We only get one type of light, one plain polarized light. It goes through, and what we find is that as the light goes through, this plane of light goes through, it gets tilted. And the degree of rotation is measured for each optical isomer. Well, if one isomer rotates it one way, the other isomer will rotate it the other. It's so subtle. That's really the only way of noting the difference, is if they affect plain polarized light. Well, in organic chemistry, there's lots and lots of these types of molecules. There's really hundreds of thousands, maybe millions of them. In this type of chemistry, though, there are very few that we can deal with effectively without learning a whole bunch more. So the ones that will be optical isomers are the ones that have 3 of the ethylene diamine ligands on it. It doesn't matter what this is. If you see a metal ion with this attached, then it is going to be optically active, and you're going to have the mirror image is going to be an enantiomer. If you have a molecule and its mirror image don't overlap, then they are enantiomers. If they do overlap, then they're the exact same compound. The other one that you might see is where you have cis ethylene diamine, and these are the only 2 that are going to be optically active. Now in class I will have the molecular models and we'll go through them, and the book has good pictures. I'm not going to try to draw them here. It would take forever and they would look really bad. So your book has the information. But on the exam, if I ask you, from amongst these coordination compounds that are optically, of the ones that I'm showing you, which ones are optically active, they'll have a metal. If you see that, then that's optically active. Actually, I drew them out here. I showed the formulas. If you see something like that, if this is cobalt or iron, doesn't matter what the metal is. If it has 3 ethylene diamines, optically active. If it's cis and you have a metal, 2 ethylene diamines, and then whatever these are, this could be chlorine, hydroxo, it doesn't matter. This is optically active. And that's it. That's it for us. There's others, but for us, that's all you see. So all the rest of them that you see will be optically inactive, will just be regular molecules.